My name is Keshwani. That's Keshwani, Keshwani. We are here because we want to prepare for the GMAT. We have been solving GMAT math problems out of this book here, GMAT Review, the official guide, the 13th edition. If you do not own this book already, purchase one immediately. You're going to need it. The book contains 230 problem solving questions. It has 174 data sufficiency questions. We already solved every single math problem from this book. If you're interested in watching the original solutions to any one of the problems, you will find the original solutions from day number 1 through 250. Right now we are in the process of redoing the problems and we are on page number 174. Please turn to it. Page number 174, the very first problem on the page, number 155. Let's see what it has to say. Number 155 tells us that y is the smallest positive integer such that 3150 times y happens to be a square such that it happens to be a square of an integer. Now, what does it mean, square of an integer? Say, for example, the integer that we're talking about, the square of an integer, let's call this integer z. So what they're telling us is this amount that we have here, 3150 times y, happens to be a square of an integer, and if you were to call that integer z, then this amount is equal to z squared. What they're telling us in a very roundabout way, what they're telling us in a very awkward way, is that this amount that we're looking at, what they're telling us is that it is a perfect square. This amount is a perfect square. 3150 times some other integer has to come out to be a perfect square. The question is, what is the smallest value that we can think of which will make this thing happen? Which will make this quantity to be a perfect square? Let's find out, shall we? Let's find out. We have 3150 here, 3150. Let's break it up into 315 and 10 so that we don't have to deal with the huge number together. Let's break it up into 10 and see what. Break it up into two parts here. 315 times 10 is going to be 3150. Let's find the factors of 315 first. 315 here we see, even though it ends in a 5 and we know this is divisible by 5, but the convention, the rule dictates that we try to divide this number by the smallest prime number possible. The smallest prime number possible here, obviously we can't divide it by 2, it's not an even number. But if you look at the sum of the digits here is 1 plus 5, which is 6, and this is 3. Of course, 6 is divisible by 3 and so is 3, which means this number, 315, is divisible by 3. Let's divide it by 3 instead of 5. How many 3's in a 3? 3 has 1 3. How many 3's in a 1? 1 has no 3's. That 1 is going to go and join the 5, becomes 15. And how many 3's in a 15? 15 has 5 3's. Again, 1 plus 5 is 6. Since the sum of the digits is divisible by 3, sum of the digits is 6, and 6 is 6 divisible by 3. 105 is divisible by 3. Let's divide it by 3 one more time. How many 3's in a 1? 1 has no 3's. 1 has no 3's. That 1 goes and joins the 0 and becomes 10. How many 3's in a 10? 10 has 3 3's. 3 3's are 9. 3 3's are 9. The remaining one goes and joins the 5, becomes 15. How many 3's in a 15? 15 has 5 3's. Now we can no longer divide it by 3 because 3 plus 5 is 8 and 8 is not divisible by 3. Let's divide it by 5. If we divide it by 5, we get a 7, and that's where the story ends. That's the end of the story because 7 is the prime number. That's the end of that story. Let's look at that story. So let's look at Act 2. That was Act 1. And this is simply 2 times 5. So what we find here, keep listening, okay? We're getting very close to the punchline. So what we find here, what we determine here is that 3115 can be written as 3 times 3 times 3 times 5 times 5 times 7 times 7 So that was the first quantity. This was the 315 times 2 times 5. 2 times 5, which was times 10. 10 times 315. Which of course, this quantity of course in turn can be written as, 3 times 3, which is a perfect square. Then we have a 5 here, and we have a 5 here. So we can write that as 5 times 5. That takes care of that part. And now we are left with, I'm going to change the color so it's easier for us to see. We are left with 7 and a 2 times 14. What can we multiply? What's the smallest integer that you can think of? That's the question. Listen very carefully. What's the smallest integer that you can think of that you can multiply 14 by and turn it into a perfect square? Can you multiply 14 by 2? 14 times 2 is 28. Is 28 is a perfect square? The answer is no. The answer is going to be no all the way through. The answer is going to be all the way through because 14 is simply 2 times 7. The only way you can convert this into a perfect square is to multiply it by another 14 and we'll end up with 2 times, this should say times, not a plus. 2 times 7. Or let me do it on this on the same line. The only way we can convert this into a perfect square is to multiply it by 14 and we'll end up with 2 times 7 again, and 2 times 2 is a perfect square and 7 times 7 is a perfect square. So the question here was, well, what's the smallest value of y? What's the smallest value of y that would work here? The answer is smallest value of y that we need here is 14. Because 14 times 14 would be a perfect square, 5 times 5 is a perfect square, and 3 times 3 is a perfect square. Hence, our y that we're looking for has to be 14. Y equals 14. That's all. We're done. Let's go on to the next one. I think I've done it again. Explained too much, probably. Can't help it, you see. Let's go to the next one. Number 156. Just give me one quick second for my break. $156. $156 actually, the one that we are about to do, number 156 actually is very similar to, a problem that we have already done, which is the data sufficiency problem, number 96 on page 283, which we did it on day number 298. We have already done this problem on day number 298. We are at day number 327. If you watch 298, day 298, in that video, we did this problem, data sufficiency number 96, and I want you to compare that problem. with the problem that we are about to do. They are very similar. Let's see what this problem says actually. It says x represents the greatest integer less than or equal to x. Alright, let's see what we can do. I need the room, obviously we need to erase everything. Otherwise it gets too crowded. By the way, these are some of the words that we must have learned in the previous video, in the last video, which was day number 325, or perhaps even 323 or 321, I don't know, in the last couple of days. We came across these three words in the lecture, and I never had a chance to actually look them up to tell you when we learned these words. The word digress is a very simple word for a native speaker. It's a word that we learned on day number 3 of our vocabulary lesson. The nub, N-U-B, nub, is something that we learned on day number 11, and accentuate is something that we learned on day number 40. Just type in GMAT words, day number 40, and the video will pop right up. So, what does it mean? X represents the greatest integer less than or equal to x. For example, can you tell me what will be the value of this quantity? 5.3. If 5.3 appears in this symbol there and then in this box like this, then it is to represent the greatest integer that you can think of. We have to be able to think of the largest possible integer that we can find, which is either equal to or less than 5.3. Is it equal to this? Is that the largest integer that we can think of, which is either equal to or less than 5.3? The answer, of course, is no. The largest integer that we can think of is 5, which is either less than or equal to. Of course, it's not equal to, but 5 is the answer here. It's not 6. When we see 5.3 in the box, it does not equal 6 because it cannot be greater than, it has to be less than or equal to what we see in the box. Let's do one more. It has to be less than or equal to what we see in the box. For example, how about this one? What's the largest integer that we can think of that is either less than or equal to -2? The largest integer that we can find that is equal to -2 is -2. How about this one? 2.1. What's the largest integer that we can find that is either less than or equal to? It cannot be more than -2.5. It cannot be more than -2.5. Therefore, the largest integer that we can find that's going to be less than -2.1 is -3. Let's do one more. How about this one? -4.7. -4.7, of course, is going to be -4. Yes, you're absolutely right. That's wrong, isn't it? Absolutely right. You're absolutely right. It is wrong. The largest integer that we can find that is less than -4.7 is not -4. -4 is actually more than -4.7. This answer is wrong. It is -5. Now that we understand what they're looking at, now that we understand what they're talking about, let's do the problem. Enough of the talk, let's do the problem. Where can we do the problem? We can do the problem right here, if you like. We can do the problem right here. -1.6. What's the largest integer that we can find that is less than or equal to -1.6? The largest integer that we can find that is less than -1.6 is -2. Equal to part does not play a role here. Equal to part does not play a role here because it's 1.6, it's not an integer. So it can't be equal to. Then we have 3.4. What's the largest integer that we can find that is less than 3.4? The largest integer that we can find that is less than 3.4 is 3. Similarly, the very last one we have is 2.7. What's the largest integer that we can find that is less than 2.7? Again, equal to part does not play any role here. Equal to part is not going to play a role here because it cannot be equal to it because this is not an integer. It has to be an integer. This represents the greatest integer. It has to be a whole number. So equal to part is not going to play any role here. So the largest integer that we can find, the greatest integer that we can find that happens to be less than 2.7 is 2. That's it, we're done. So we have a -2 plus a 3 plus a +2. -2 and a +2 are going to kill each other, and the answer is 3. Answer to the problem is 3. Let's do the next one, shall we? 157. Number 157. I need my break as usual. Number 157. In 157 we are told that 4 minus x over 2 plus x equals x. And the question is, what's the value of this guy? X squared plus 3x minus 4 equals what? Well, let's see what we can do, shall we? Let's see what we can do. Let's cross multiply both sides. We'll cross multiply both sides by 2 plus x, so we end up with 4 minus x equals x times 2 plus x. And let's just see what happens. Let's just see what it gets us. Open the parentheses, we get 2 times x, and we get x squared. We get 4 minus x here. Let's bring everything on this side here. So let's add x to both sides. So we can get rid of this x, is gone. 2x plus x is 3x. And let's bring 4 to the other side. Subtract 4 from here and subtract 4 from here. So we can get rid of this 4. And we end up with 3x. And then x squared plus x squared. And then minus 4 equals. And what are we left here? We're left with nothing. And what do we see? Do we recognize this thing? This thing is same as 3x plus x squared minus 4 is same as x squared plus 3x and a minus 4, which we just found is 0. That's it. The answer is 0. The answer is a big fat 0. Not a regular one, a big fat one. Let's do the next one. Number 158. Number 158. Number 158, we are told to find, essentially what it says is that on the first week Nancy saved $1, we are told. On the first week she saved $1. Then we are told that in each of the next 51 weeks, in the first week Nancy happened to save $1. In each of the next 51 weeks, we are told, she saved $1 more than she had saved the week before. So the week number 2 she saved $2, week number 3 she saved $3, week number 4 she saved $4, and so on and so forth, all the way up to 52 weeks. The very last week she saved $52. The question simply is, if she were to follow this pattern, if she were to follow this regiment, the question is, what will be her total savings at the end of the 52 weeks? Let's find out. Essentially what they're looking for here is the sum of the integers from 1 through 52. That's what we need here. What we need in number 158, what we need here is sum of the integers 1 to 52. That's what it is. Now, there is a geeky way, there is a nerdy way, a classical way, traditional way, orthodox way, academic way to do this problem, which is to use a formula. There is a formula which will give us the sum of these numbers 1 through 52, like that. But you have to know the formula, and I don't know the bloody thing. And since I don't know it, I can't expect you to know it. I just don't know it. I don't go around memorizing formulas. Do you understand? I just don't do it. We're just going to do it out manually by brute force. Okay? Now when I say brute force, even though I do use the term brute force, but there is a difference between brute force with a dose of insanity and a brute force with some sort of a strategy. You understand? That's a fine line between insanity and strategy. Let's see what we can do. Let's add up, even though there is no 0 here, there is no 0 there, but I'm just putting it there, you will see in a second why. Let's add up the first 9 days. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. This part we do have to do. There is no choice. We do have to add them up to see what it is, which is very simple. I'm going to show you why it's very simple. 1 plus 9 is 10. 2 plus 8 is another 10. 3 plus 7 is another 10. 4 plus 6 is another 10. You see that? So there are 4 tens. 10, 20, 30, 40, and then 5. It's very simple. If you have to add up 1 through 9, it's just 45. Because 1 through 9, you will have a 1 in the beginning and 9 at the end. That's a 10. Then you will have 2 and an 8. That's another 10. Then we have 3 and a 7. That's another 10. So this is what I mean by, even though I said that we're going to do it with a brute force, but there is a nuance. There is a matter of nuance between doing it with a due dose of insanity or strategy. Do you understand? So that's 45. Now let's add up 10, 11, 12, 13, and so on and so forth, all the way up to 19. Now when we do that, what do you suppose is going to happen? Do you see any kind of strategy here? Do you see any kind of pattern here? The very first one here is 10, which is 10 more than 0. The next one we have is 11, which is 10 more than 1. The next one we have is 12, which is 10 more than 2, so on and so forth. There are 10 numbers here written out here, and each one of them is exactly 10 more than the previous one, in the previous series. So we're going to have here 45 plus 10 tens. Because 1 10 here, another 10 here, there are 10 tens. Let's do the next one. So we start at 19, we begin our story with 20. 20 plus 21 plus 23, rather 22 plus 23. And so forth. What do you notice? Compare this series with the original series. We have a 0 here, we have a 20 here. We have a 1 here, we have a 21 here. We have a 2 here, we have a 22 here. You get the idea. It's the same exact series as before. It's going to be 45 plus 10 20s. We are going to have 10 20s. Let's continue. Then we'll have 30 plus 31 plus 32 plus 33, so on and so forth, which is going to be 45 plus 10 30s. 10 30s, you got it. 10 30s. 45 plus 10 30s. That brings us up all the way up to 39. This was 29. We have to go one more up to 49. So it will be 40 plus 41 plus 42 plus... And of course, had it been a real exam right now, I wouldn't go into such a leisurely way, you understand? Once you understand the concept, it goes like that. So it's going to be 45 plus 10 40s. 10 40s. We're almost done. And then, of course, this stops at 49. Of course, we still have to take care of 50, 51, and 52, which we have no choice but to do it separately, actually adding it up by brute force, which is actually not a lot of brute force. You understand? It's just 3 and 150. So we have to add these up separately. Well, let's just take care of this part. What we find here is, let me change the color so we can see it here. What we find here is, we have 1, 2, 3, 4, 5. We have 5 45s. 5 45s. We will have 5 45s. 5 45s. We know 10 45s are 450. 10 45s are 450. Therefore, 5 45 should be half of 450, which is 425. 400, or rather 225. Half of 450. And then how many 10s we have? Let's find out how many 10s we have. We have 10 tens, 10 plus 20 is 30, 30 plus 30 is 60, 60 plus 40 is 100. Aren't they nice? Aren't they nice? It comes out to be exactly 100, not 90, not 85, not 87, exactly 100. As I always remind you, these questions are written in a very clever way. A lot of thinking, a lot of planning, a lot of thought goes into writing these questions. These questions are not written willy-nilly. These numbers that you see in any problem that you see there, the numbers are there by design. A great deal of thought goes into writing these questions. Do you understand? And they are there by design. So it's exactly 100. 10 plus 20 is 30, 30 plus 30 is 60, 60 plus 40 is 100. It's just 100. It's just it's going to be 100 times 10, which is 1000. Stay with me in the story. Stay with me in the story, okay? We are almost done. We are almost done. So this thing ends at a 5. This thing ends in a 5. This thing ends in a 3. Before we do any work at all, before we waste our time, let's see how many answer choices do not end in an 8. The correct answer, whatever it is, has to end in a 5 plus a 3, which is an 8. The correct answer must end in an 8. Let's cross out all the answer choices that do not end in an 8. And there are answer choices A, B, C, D, and E. Voila. The answer is C. That's the only one that ends in an 8. All the others end in something other than 8. They cannot possibly be the right answer. We need a number that ends in an 8. Here, this thing ends in a 5, and this thing ends in a 3. Do you understand? Now, in reality, listen to me very carefully. I'm going to take a few more seconds still to make you understand what I would have done had this question been, had I been doing this problem in the real exam, and if I were pressed for time. If I were pressed for time, I'm speaking hypothetically, because right now I'm not pressed for time. We're not doing it for real exam. But had it been a real exam, and if I were pressed for time, even this work is too much. This is what you have to understand here. This is what you have to understand. These are just multiples of 10. This part, listen very carefully, these are just multiples of 10. They're going to end in a 0. They play no role. When we try to identify unit digit, they play no role. And these are 5 5s. 5 5s, we don't have to spend all this time to find out we don't have to spend all these times that when you add up 5 5s, 1, 2, 3, 4, 5, 5 5 should end in a 5. And this ends in a 3. Therefore, the correct answer must end in 8. And that's it. There are 2 more problems on this page. I'm debating whether or not I should continue doing this thing. It has already been a very long video. I'm going to stop right here, I think. Okay? I'll see you tomorrow, okay? Bye now.